Hello everyone, welcome to Power Electronics lab number 6B. Today we are going to simulate the controlled half wave rectifier with RL load. So this is the circuit schematic which we are going to follow. Now let's start implementing this circuit in LTspice. So in the last video of SCR half wave rectifier with resistive load, I have told you all how to add a model file of SCR, right? So kindly refer that video if you have not watched it to add the model file. So I've already done that and now I'll be building the circuit. So I've already selected the SCR. Now I'll go to library and type voltage. So I have to require two voltage sources, one for the anode and one for the gate. So I'll place it over here, one and another one over here. Alright. Next, I'll also require a resistor and an inductor in series with it as a load. Okay, so these are the main components in the circuit. Now I've connected them with the wire. So let's start connecting them with the wire. This is acting as a load. This is my anode supply. And remember, the supply connected to the load has to be connected not to the ground but to the cathode, to the gate terminal, to the cathode, right? So also one more thing is the ground. Don't forget the ground. So let me push the circuit slightly up, yeah, and let us add the ground now. So our circuit is complete. Now we have to plug in the values of the voltages and the resistor and inductor. So as per our requirement, we will let us check it out over here. Okay, so as per our requirement, we will require a resistance of 5 ohms and inductance of 6 millihenry, whereas a V in peak value will be 50 volt for 50 hertz, right? So AC supply will be 50 hertz. So your RMS value will be around, it will be V in peak upon root 2, that will be around 35.35 AC, right? So if you want to say we have applied a single phase AC supply of 35.35 value, RMS value, right? So since the frequency is 50 hertz, the period of the AC input voltage will be around 20 milliseconds, right? So let's plug in these values and let us continue with the simulation. Yeah. So over here, this is my source voltage. So I'll right click over here, go to advanced and select sine, right? And right over here, DC upset is 0. Amplitude, well, we have to give around 50 peak value and the frequency is around 50. Click on OK. So your anode supply voltage has been applied as 50 volts peak value. Now we have to see the gate voltage. So at the gate we have to apply a pulse, right? Remember, to turn on the SCR, yeah, let us concentrate on the screen. To turn on the SCR has to be in the forward blocking mode and we have to apply a small impulse. Not a gate pulse, not a long gate pulse, but an impulse, small gate impulse, right? It should be on for a very short duration of time and then it will be off. Throughout negative half cycle of the input, it should be off. Only during the positive half cycle of the input, we should apply this gate impulse. So to apply this gate impulse, we have to give a gate voltage, right? So let's start doing that. So I'll select over here, right click, go to advanced, go to pulse. Even though it's written pulse, we'll apply a small impulse. Initial value over here is 0. Let's say the on value is around 3 volt. Delay. Now how will you decide the delay? So let us go back over here. Let me explain it to you with an example. The concept of firing angle or time delay over here. How we'll decide the alpha, right? And at what particular time in the x-axis. So let us check it out. Wait, it's taking some time to load. Okay, so basically your 0 to 2 pi will be 0 to 360. That means 0 to pi will be 0 to 180 degree. Yeah, it has come now, I guess. No, not yet. Yeah. So 0 to pi will be around 0 to 180 degree, right? So if I have to select a firing angle, I mean, let's say in our case the time period is around 20 millisecond, right? So 0 to pi will be around 0 to 10 millisecond. So if I want to select a firing angle of alpha, directly I have to select half of it, right? So half of 10 will be 5 millisecond. And for 45 degree, 45 degrees firing angle, I have to take the half of 5, that will be 2.5. Let me explain with an example. Hope it is, no, it has still not come. Let me just refresh this part. Okay, it has come now. Yeah. So this is what I was saying. Since a period is around 20 millisecond, the half the period will be around 10 millisecond. So in that half the period during positive half cycle, if I select 5 millisecond as my time period, that is a delay, my alpha will be 90, right? So if I have to select alpha as 45, I have to select time delay as 2.5 millisecond, right? So that's how we get this as 2.5. So your alpha will be 2.5 then, right? This alpha will be 2.5. So let us do that thing in the simulation. So in the pulse, the time delay will be 2.5 millisecond, right? The rise time will be 1 nano, fall time also will be 1 nanoseconds. The on time, I want this gate pulse to be on for a very short time. Here it is. Yeah. This gate pulse should start at 2.5 milliseconds and it would last for, let's say, 1 millisecond only, not more than that, right? Because this is enough to turn on the SCR. Okay, so this T on time will be around 1 millisecond and the total time period will be 20 millisecond. I'll click on OK and I push this a little down so that it doesn't coincide with inductance value. Now, inductance value, resistance value was given as 5 ohm and inductance value was around 6 millihenry. Okay, so I've given all the values over here. Now we have to start simulating the circuit. So I'll click on simulate. Before doing that, let us label the circuit, right? So here I will call this as in. It is the input voltage, right? So this will be out, right? And this will be gate voltage with respect to cathode, and cathode we have called it as out, right? Yeah. So now I have labeled the circuit, right? Now I'll go to simulate, click on run. Now over here, I'll maximize the blank screen, right? Now right click over here, click on add trace and type over here V in. That will plot my V in. So we have 3 cycles, right? And actually we have already given the transient step time as, let me delete and show it to you first. Let me rerun the step. So after you have completed the circuit, you have to click on simulate and click on run. It will ask, we have to do the transient analysis because we are plotting V in versus time and V out versus time and the current pulses also. So everything is with respect to time. Now the stop time, how to decide the stop time? One period is 20 millisecond. So let's say if I want to view 3 cycles, I can give it over here 60 milliseconds and I click on OK. So then the screen will appear. I have to maximize that. Right click, add trace, and I plot V in. V in with respect to ground. So this is what I have, right? 50 volts peak value, and your time period will be, one time period will be around 20 millisecond, and we have 3 cycles over here, right? Next, I'll right click over here, add a plane plot. I'll actually add 4 plane plots now. And I push this at the top, V in at the top. Next, I want to plot this V out with respect to ground. So I'll right click over here, add trace, click on V out. Okay, so this is my V out, right? This is my V out value. So this V out, I can merge it with either V in, right? So that will be clear, no problem at all, right? We can easily see that V in is black color and V out is blue color, right? So we can see the distinguish, or we can keep it same, right? Next, I want to plot the gate voltage across the, the SCR voltage, right? So I have to plot V, this anode voltage with respect to cathode. So I'll place one terminal over here and another with respect to this. So this will be my SCR voltage. Okay, this is my SCR voltage. What I've done is I've placed one probe over here, voltage probe, and with respect to that I've placed one another probe over here, anode to cathode. So anode to cathode voltage is nothing but my voltage across the SCR, and which is showing over here, right? So this is my voltage across the SCR, and now I want to plot the current. So for the current, I can plot over here, right click on add trace, and either you can plot I of R1 or I of L1, right? Both are in series. So let's plot I of L1. So this is my current which is flowing into the load, right? This is my load current. Now, lastly, I also want to add one more plane plot. So let us push this slightly up, V in and V out, then voltage across the SCR, the current through the load. Now I want to plot the gate voltage, right? So gate voltage is plotted with respect to cathode voltage. Yeah. So here, this is what I have done. So this is my gate voltage, which I have applied, right? At starting at 2.5 millisecond, lasting for 1 millisecond, and its amplitude is around 3 volt, right? Now, correspondingly, I will require the gate current. We talked about gate current, right? So just bring it over here. I mean, we can right click also on the blank screen, one of the plots, click on add trace and see over here gate current, right? So this is my gate current, right? Corresponding to my gate voltage being applied, there is a gate current being generated of amplitude of around 420 odd milliamperes, right? So this is my firing angle. These are my gate trigger pulses, and as you can see, these gate trigger pulses are only active during the positive half cycle of the input, not during the negative half cycle, because in negative half cycle the SCR will be off. Okay. So these are the waveforms of a half wave rectifier with RL load. Now let us compare these waveforms with what we have discussed in the theory. So let me keep half screen over here and another one over here. So I can compare it. Okay. Okay, yeah. So this is my input, and this black color thing is my input over here, V in. My V out looks something like this. It is exactly as it is shown over here, right? Correct. So this is my V out. The behavior is slightly, similar to what we have observed, right? There's a slight glitch over here. That is okay. That is fine. That depends upon, we have to fine tune the value of the inductance. Then there is a voltage across the SCR as shown over here, right? Again, there is a glitch. Kindly ignore that part, right? And yeah, this is my voltage across the SCR. Then my load current will be here. The behavior of the load current is here, right? It's conducting beyond pi value, right? And it's stopping over here, right? And these are my gate pulses. Now I've also showed the gate voltage. I want to show you all what we have applied and what we get at the output of, at the gate terminal. So this is my gate pulse which I've applied, right? Now, yeah, so the waveforms are coming out to be accurate enough, right? There is no problem in it. Now, let us go back to the part wherein we have to calculate certain things. For this, controlled half wave rectifier with RL load, right? So there are various parameters which we have to control. So first of all, we have set the firing angle as 45 degrees. How we have set the firing angle as 45 degrees? As you can see, if I place my cursor over here, it's going to start over here at around, exactly at around 2.5 millisecond, right? So we have calculated before, for time delay as 2.5 millisecond, my firing angle will be 45 degrees, right? So if I want to calculate this formally, what I can do is, I know that I'll do the calculation of alpha, and we will call it as a beta also later on. I'll explain what is beta, right? So alpha is the firing angle or a delay angle for the SCR, so that it turns on. So alpha is 90 degrees at t equal to 1 millisecond. At t equal to 5 millisecond, right? We have seen that before. Alpha is equal to 90 degree at t equal to 5 millisecond. So at alpha equal to 1 degree will be at how many milliseconds? So we can cross multiply and check. So for x milliseconds, we will have 0.00. For 1 degree, we will have 0.055 milliseconds time delay, right? So since our time delay is 2.5 milliseconds, we'll calculate alpha. For time delay 5 millisecond, alpha is 90. So we'll cross multiply and we got the value of alpha as 45 degrees. So this alpha is around 45, firing angle is around 45 degrees, right? Now from the waveforms, if you see carefully, let me show you the waveforms part now. Let us maximize this part. Yeah. So the current value goes beyond the pi value, right? The positive half cycle, and the current value even continues when the input is negative. Now that happens because the inductor which is there, which stored the energy, now it's acting as a current source and give the energy back along with the supply, right? So it is releasing the stored energy. Due to that, what will happen? The current will still continue even though the voltage is going negative, right? So this reason you can concentrate a little more, focus on little more in the theory part. But due to that, whenever the current becomes zero, that point we call it as beta, right? So this beta we have to also calculate. So let us check it out in a waveforms. Where is the current going zero? So let me go to current waveform over here and let me maximize this part. So let's say I'll note down this time. If I bring my cursor over here and put the cursor over here like this. So this is the time around 11.05 milliseconds. So for a delay, time delay of 11.05 milliseconds, I have to calculate the value of beta. 11.1 or 11 point, we can, it's up upon us how do we take it. Okay, here it is 11.12, right? So at t equal to 11.12 or t equal to 11.1 millisecond, we have to calculate the value of beta. So we know for beta equal to 90 degree, the time delay t dash will be around 5 millisecond. So what will be the value of beta at 11.1 millisecond, right? So this beta value will be, we can cross multiply and check it out. Its beta value is coming out to be 199.8 degrees. So we can clearly see that around here we will get 180 degree, right? Around this point. Around this point we can get 180 degree and we can clearly see the current continuing further than this 180 degree, even when the input is going negative, right? That is because of the RL load. So this is how you calculate the value of beta. Now, let us check out the other calculations which are there in our observation table. So observation table for firing angle alpha, we have taken sample as 45 degrees, right? So we have to just check the value of V out average, V out RMS simulated and calculated, then V in RMS simulated and calculated, right? V in RMS we have calculated already. It's 35.355 volt. Now, how you calculate V in RMS value? So here what you can do is you select this V in, press Control and left click. So again I repeat, press Control, once you select the value of V in, press Control and left click. So it will give you the average value. Of course, the average value of the AC signal will be 0. It's very small microvolt. So average value of AC signal will be 0. RMS value is coming out to be 35.354. So that is what we have written over here in red color, right? Next, similarly, we wish to observe the average and the RMS value of the output. So again, I'll select the output, press Control button and left click on it. So this will give me the average and the RMS value all together. So the average value of this output waveform is around 12 point, the simulated value will be around 12.781. That is what we have written over here, right? And the RMS value is coming out to be 23.51 volt. Here also it is 23.51 volt. Okay, correct? And yeah, now that is how you calculate the RMS and the average value of the output waveform from simulation. Now let us close this and let us focus on this part over here, right? Let us focus attention in calculation. Okay, so you can derive this V out average formula. We are not going into that. We are using this formula now. So it is given by V out average will be given by Vm by 2 pi into cos alpha minus cos beta, right? So over here Vm is 50, alpha is 45, beta is 199.8. So we'll plug in the values over here. 50 divided by 2 pi into cos 45 is around 0.7071 and cos 199.8 is around minus 0.94048, right? So if you calculate this and plug in the values in the calculator, you will get it around as 13.11 volt, right? So if you compare it with the simulated value of V out average, the value is quite close. Its simulated value is 12.78 and calculated value is coming out to be 13.11. Alright. Now let us go and calculate the V out RMS calculated value. So this is a quite a quick conversion between degrees to radians. So 1 degree will be multiplied by pi by 180, that will be equal to 0.017 radians, right? So 90 degree will be about pi by 2 radians, that will be around 1.57 radians, right? Here this is the formula. V out RMS will be equal to Vm by 2 into 1 upon pi the whole into beta minus alpha plus sine 2 alpha upon 2 minus sine 2 beta upon 2, right? Bracket close and whole raised to half, right? So here we have to calculate sine 2 alpha. Sine 2 alpha is coming out to be sine 2 into 45, that will be sine 90 and sine 90 is 1. Sine 2 beta will be sine into 2 into 199.8 and that comes out to be, if you plug in the calculator, 0.6374, right? So here we have the value of, remember, here the value of alpha and beta will be in radians, right? When it is not used with sine, right? Either sine to alpha or sine to beta. This value will be in radians. So let's convert alpha and beta into radians. Alpha is 45 degrees. So 45 into pi by 180, that will give you 0.7854 radians. And beta value is around 199 degrees multiplied by pi by 180. That will give you 3.487 radians. So we'll plug in the values over here. 3.487 minus 0.7854 will give you 2.7416, right? So this is the value. Sine 2 alpha upon 2 will be 0.5 because sine 2 alpha is around 1, which is coming, and this will be sine 2 beta upon twice, that will be around half of this, that is 0.3187, right? We plug in all the values over here, we finally get this will be 25 into 1 upon pi into 2.9229, the whole raised to zero point 0.5. So if you plug in finally in the calculator, you will get the value of V out RMS calculated as 24.11, right? So let us compare it with the simulated value. Give it some time. Yeah. So we have calculated all the values, almost. We have left out with the power factor calculation. All right. You can go through the derivation. We are not concentrating on how we got this formula of V out RMS. We are just using the formula and so that we can compare it with the values obtained via simulation. So just give it some time. It is actually taking some time to load. Let me refresh this. Hopefully it will come up. Okay. Okay, fine. Let us wait for that. And also, in this simulation, there is one more thing. What you need to do is, whatever we have done, we have to do it for the alpha value of 60 degrees, right? So how will you change the alpha value to 60 degrees? What will you do? Yes, you will change the delay time, right? So I have shown you all how to calculate the delay time for alpha value, which we have decided for 45 degrees, for example. Now you have to set it for 60 degrees. So for 60 degree, what will be the time delay? You have to calculate that on your own. Okay, fine. So you have to repeat this entire thing for 60 degree firing angle and calculate V out average, V out RMS, V in RMS, then the load current waveform, and also the power factor, which we have to find out, right? It's taking some time to load again. Let us wait for that till that time. Yeah. So now next thing is that there is some concept of this is something more than what I have explained that in the experiment. So this is about the freewheeling diode, right? So what do you mean by freewheeling diode? Basically, we place a diode in in parallel with the load. That is a concept of a freewheeling diode, right? So what it will do, freewheeling diode, what it will do, it will just make the waveform which was going negative in our previous case, which we have seen over here. Let me open the Microsoft OneNote again. So earlier it was going to voltage waveform was going beyond negative value. With the freewheeling diode, it won't go, right? Even though the continues to flow in the load. Yeah, here it is. Yeah, sorry for the dusting. So V out RMS was coming out to be 24.11 volt, and the simulated value we came out to be 23.51 volt. Let me complete the power factor part. So power factor formula will be V out RMS upon V in RMS. So first we calculate the simulated value. So we substitute the simulated values of V out RMS, that is 23.51, and simulated value of V in RMS, that is 35.354. We get a power factor of 0.665, which is not very good. And for power factor calculated value, we substitute the calculated values of V out RMS and V in RMS. So V in RMS simulated value, sorry, I think it is reversed. The simulated, this is the calculated value, and this earlier one was the simulated value, right? We substitute the calculated value over here now. So that come out to be 35.355, and V out RMS calculated value is around 23. Simulated value, I think we have done something wrong. Yeah, we have done something wrong. Let me just change it. So over here we have to substitute the calculated value. So I guess I have done it the simulated value. Let me take it out. Whether these values are proper. Okay, so it will be, instead of 23.55, 23.51, it will be 24.11 divided by 35.355, right? So this power factor comes out to be 0.681. Instead of this value, it will be 0.681. Please note down that change. Okay, so this won't be coming over here. It will be actually, yeah. Let me just add it on. Add it over here. This value will be 0.681, right? Why? Because this value of V out RMS have substituted it incorrectly. That should be 24.11. Instead of 23.51, it will be 24.11. Rest denominator is fine. So the power factor is coming out to be 0.681, right? That is quite close to simulated value of 0.665. Why I said the poor power factor? Because power factor should be ideally equal to 1, and it's way beyond, far off from the value of 1, right? Okay, so now this completes the experiment part. Now let me show you one more thing. There might be a question in your post lab that what is the effect of freewheeling diode on the circuit, right? So if I add a freewheeling diode in parallel with the load, what will happen? Okay, so do you see this negative energy, negative V out value? This negative V out value, if you don't want your V out value to go negative, we have to apply a freewheeling action, right? So let me show it to you that. So let us go to the components and type diode. So I have to add it in a reverse direction. So I'll press Ctrl R. I have placed the diode, and let me add it in the parallel manner to the load. Now I'll select, right click on the diode, and I have to select the power diode, right, with a higher rating. So I right click over here, click on pick a new diode, and there I'll search for a diode with a higher breakdown voltage. That will be a power diode. Okay, I'm scrolling down. So here it is the type rectifier type diode. So as you can see, I see for 750 volts is the breakdown value. So I'll select this diode. I click on OK, right? Now I have this diode will act as a freewheeling diode. So during the negative half cycle of the input, when the inductor was returning the energy to the load, this time what will happen is the inductor energy will be released via this diode itself, right? So the voltage value will be positive. So now if this was the waveforms without freewheeling diode, Now this negative part which is going, V in value negative which is going over here, this will not happen. It will stay a positive value. Here it is, right? So let me show that. I'll go to simulate, click on run. So you see the effect? The V in is not going negative at all. It's staying over there at positive value. Even though the current is dying out and becoming zero, still it's becoming zero at around beta value only, but it's dying out fast, as you can see. Because what really happens is during the negative half cycle, the inductor energy stored will be released in this freewheeling diode part, right? So freewheeling diode will freewheel all the energy which was present in the inductor. So the current will die out very fast to zero, and the voltage, output voltage, the load voltage won't go to negative. It will be staying positive. So that's the effect of the freewheeling diode on a controlled half wave rectifier, right? So that will be all from my side. We have completed this the simulation of a half wave control rectifier with RL load, right? So you all can play around with the values of R and L, and also with the values of the delay and delay time, so that we can control the firing angle and you can get the desired output voltage, right? And also we have seen the effect of the freewheeling diode on the output waveform. So that's it for this lab session. Next time we'll start with full wave control rectifier. So until then, have a good day and thank you.